Greetings, it's Paul Bamberg with the introductory video for Class 11 of Math 117. This whole class is a bit of an aside. I want to go through some very standard examples from elementary probability theory of positive random variables, but look at them in the manner introduced by Deneen that I introduced last time, showing you how these can be approximated by sequences of positive bounded random variables, and in turn then by sequences of simple random variables. So here's a review. We've got a random variable that is positive but not bounded. You recall we can make it bounded by saying that if the random variable would have a value in excess of the integer m, we will set its value equal to m. Each xm is now a positive bounded random variable. We know how to calculate its expectation, and we define the expectation of x itself to be the limit of that quantity as m approaches infinity. I will be doing this limiting process for 3 or 4 different examples shortly. When we do that, the limit of expectations is the expectation of the limit, the expectation of a sum is the sum of the expectations, and the obvious order properties hold for expectations also. You saw that last time. So let's look at some concrete examples. My first one is going to be the distribution known as the geometric distribution. Here's a concrete example that gives rise to the geometric distribution. You go to job interviews, and your plan is you will continue interviewing until someone says yes to you, and then you stop interviewing. At each interview, the probability that you'll be offered a job is p. This is constant for all interviews, and so the probability for a no is 1 minus p, which I'll denote by q. What's the sample space here? It consists of all sequences that contain k symbols in all, with the first k minus one of them being no's and the last one being yes. The sigma field is 2 to the omega. That's a pretty big sigma field because there are sequences in here that are arbitrarily long. What's our probability function? It assigns to the event. You finally get a yes on the kth interview. The probability q to the k minus 1. That means you've got k minus 1 no's times p for the yes. What's the obvious random variable? It converts the element of the sample space into the length of the string, the total number of interviews, and the probability that the random variable has the value k is therefore q to the k minus 1 times p. I'm sure you've seen examples like this before. Now, a problem with that random variable is that it's unbounded. There's no guaranteed upper limit to the number of interviews, but maybe the Office of Career Services has decided to help you out. They've decided if you have m unsuccessful interviews, you will be offered a job with the Office of Career Services. So now we have turned the random variable x into a bounded random variable, xm, where the probability of this new random variable for m is the probability simply that your first m minus 1 interviews were all unsuccessful. It's q to the m minus 1. That's the sum of the probabilities of getting jobs on the mth interview or beyond in the earlier unbounded random variable. Each of these random variables is simple. Furthermore, we've got an increasing sequence, and we can calculate the limit of its expectation directly, because I can actually do the sum from k equals 0 to infinity. No, I botched that. I should have said the sum from k equals 1 to infinity, shouldn't I? Okay, I picked up a virtual pen and did a crude fix. This sum should go from 1 to infinity. The sum here correctly goes from 0 to infinity. P, of course, is a constant. We take it out, and if we differentiate that sum term by term, we will get 0 as the first term from differentiating q to the 0, and then from 1 to infinity, we will get the other terms in the sum. But this is a sum that we all know. It's the sum of a geometric series. It's 1 over 1 minus q, and its derivative is 1 over 1 minus q squared. So we get p over the quantity 1 minus q squared, p over p squared. We get 1 over p. A staple of introductory probability courses. The expectation of a geometric random variable is 1 over the probability of success. Here's another example of an unbounded random variable, the Poisson distribution. This time the Office of Career Services asks you, how many interviews do you expect to need to get a job? And you give an estimate alpha. You say, oh, I think I'll probably need 6.5 interviews or so. They line up a job for you, but in order to fulfill your expectations, they also set you up for some unsuccessful interviews, and they want to do this in such a way that the expected number of interviews that you do before you get the job is alpha. How do we do this? Well, we set up the interviews and we position the successful interview as the kth interviewer with probability alpha to the k over a k factorial multiplied by e to the minus k. If you've never seen this before, it looks a little bit far-fetched. If you have seen it before, you say, oh yes, a Poisson distribution. But let me check that this is right now. What is the sum of the probabilities of getting the interviews, the successful interview, on all cases from the first interview on? Well, we've got alpha to the k over k factorial. That has to be summed from 0 to infinity. We multiply by e to the minus alpha, which is very nice because this is the Taylor expansion of e to the alpha. So the product of the two functions is 1. What's your total number of interviews? Well, your total number of interviews is a random variable, and the probability that the successful interview is the kth one is given by this Poisson distribution again. All I've done here is switch my viewpoint from the sample space to the real numbers. Now, how can we turn that into a sequence of simple random variables? We could make a simple random variable out of the Poisson distribution by saying that if you have done m interviews, you're automatically offered a job, and then we can calculate the expected number of interviews with parameter alpha by saying we'll do the sum from 0 to infinity as before, but then we'll do a correction because for all the terms where k is m plus 1 or larger, there were k minus m interviews that you didn't actually have to go to. In the limit, as m becomes very large, the contribution from all these terms goes to 0, so only the first term matters, and we can calculate the expected number of interviews by multiplying the probability that the kth interview is successful by k, and then noticing when we go to do this sum, k over k factorial is 1 over k minus 1 factorial. K minus alpha to the k minus 1 times alpha is the alpha to the k we started with, and this is precisely the sum we had before. It's the sum for the exponential function, and therefore the expectation of this Poisson random variable is alpha. You may have encountered that result before in some probability course. There's another better known way of representing the Poisson distribution as a limit of bounded random variables. You can represent it as a limit of a binomial distribution. In order to do that, we carry out some number of trials. It has to be greater than alpha, and the probability of one of those trials being successful is alpha over n. Our random variable y is the number of successes, and that number of successes is easy to calculate. We've got k successful trials, each with a probability of alpha over n. We've got n minus k unsuccessful trials, each with a probability of 1 minus alpha over n. So that's the probability of k successes followed by n minus k failures, but there are in fact n choose k ways of distributing the k successes among the n trials, so we have to multiply by this binomial coefficient. For each value of k, this probability is larger than the Poisson probability, but it's not too difficult to confirm that the limit, as n approaches infinity, of this binomial probability distribution function is the Poisson distribution function. This is a nice way of representing the Poisson distribution as a limit, but it doesn't fit in very well with our general scheme for the simple reason that this is not an increasing sequence of random variables. Now let's try something where the possible values are not limited to integers, where the possible values of the random variable are all positive real numbers. For the sake of concreteness, we'll assume that the experiment is you have somehow got hold of an unstable nucleus, like iodine-131, which has a half-life of 8 days, and the experiment is you observe it until it undergoes radioactive decay. The sample space is specified by the possible decay times, so it's the interval from 0 to infinity, and the sigma field is the Borel sets among the non-negative integers. That is the intersection of the Borel sigma field with the interval from 0 to infinity. Now in this case, the probability distribution is given by physical law. The probability that the nucleus will decay within time t of when you start observing it is given by the formula 1 minus e to the minus lambda t, and the quantity in the exponent lambda is known as the decay constant. The obvious random variable to associate with this experiment is the time at which the decay actually occurs, and so we're describing this in terms purely of real numbers, not explicitly mentioning the sample space. We say we've got a probability distribution specified by the random variable t, and the formula for it is, for this particular Borel set, its value is 1 minus e to the minus lambda t. Now how are we going to calculate the expectation of this? Well, you say, that's easy, you can do the integral from 0 to infinity. Yes, but I'd really like to look at this in terms of a sequence of bounded random variables. So this is a little bit far-fetched. If the nucleus hasn't decayed after m days, we'll contact the supplier, say, we got a bad nucleus, I want you to take it back, and they will take it back. So now the random variable can have values up to m if the nucleus decays, and the value is m if it gets taken back. Presumably, since it wasn't actually defective, it will decay at some later time while back in the custody of the supplier. We can calculate this truncated random variable's expectation as a Lebesgue integral, though, because this is a case where the situation that I described in the previous introductory lecture applies. Our probability distribution function is nicely differentiable. Its derivative is lambda e to the minus lambda t, and the expectation is the integral of that up to m plus m, the number of days we have this if the manufacturer takes it back, multiplied by e to the minus lambda m, the probability that it would decay at a later time than that if we kept custody of it. As m approaches infinity, of course, this second term goes to 0, and so the expectation of t is just the integral when we replace m by infinity, and that integral is easily evaluated. Turns out to be 1 over lambda, which physicists refer to as the mean lifetime of the nucleus. Really, the only interesting thing here is that it is possible to truncate this random variable, and as in earlier examples, it's actually a bit harder to calculate the expectation for the random variable Tm than it is for t. When we actually do the calculation, evaluating an improper integral is the way to go. So that concludes this brief exposition of how you can apply this idea of converting a positive random variable into a positive bounded random variable to some straightforward examples, which you'll have a chance to play with in the problems you'll be solving in class.